Hello and welcome everyone. Finally we have some results in from our biohacking that we have done on the Bulletproof forum. And I hope to get more results in as the time goes on here. But at least we have 2 full designs done. I think I will need to start to explain a little bit about the background of the design. We have used something called the design of experiment, and that is what DOE stands for, which I guess not everyone is familiar with. It's something used very frequently in the industry when they do test and optimize things. If you, for instance, have a new car, the engine has been optimized with design of experiments. If you will test things the old-fashioned way, you will basically be out of business. It's not good enough. And that is why we are taking these state-of-the-art techniques to the biohacking community. Let me just explain what we have done and why we haven't done it in some other way. This is an example of an optimization, so this is in the statistical literature. If you want to know more about it, if you download the PowerPoint, you can click on this link and you will come to a YouTube video where I talk like 50 minutes about this that you will get for 5 minutes here. Here we test something. And reaction, we want high yield, we change one factor, which is the time. We keep everything else constant. We find the best point here at a certain time. Then we change the next factor, which is temperature, and we keep everything else constant. We don't want to move anything, because then that will confound these results. That is true. Then we take this temperature here and this time and combine them. Then we have the optimum conditions for these chemical reactions, you might think at least. If we disregard any other factors, they are not significant in this example. Well, now we look at them one by one. We look at this one by itself and this one by itself. If we take a look at what we did here, but we look at time and temperature at the same time, we look from them above, you will see we changed one factor, we find the best result. We locked it there and changed in the other direction and found the best result. And the blue is the unknown area that we are investigating. But when we do investigate it by moving just one factor at a time, there are a lot of things that we cannot see or estimate. In this particular case, we know how it looks. This is how it looks. This is a contour plot where this is the optimum, the top of the mountain, if this would have been a map, and then you go down and down and down. Here you see the yield for each area. This is where we thought we were, but we were not in fact. But we didn't do anything wrong. If we go back and look here, we did take the best temperature and the best time. If you look at it, we changed here one by one, and this was the best point. Then we looked everything and changed in the other direction. This was the best point. It's just that if we're not lucky and start here, we won't pass the best point, and we won't understand that we haven't reached the best point. It looks like an optimum when you test one factor at a time, but in fact it isn't, unless you're lucky. The same would be true if we had started with this factor first. It would have ended up here as the best point and then gone in this direction. It would have ended up here, somewhat better. But it all has to do with chance, random. The results are random, depending on which order you do the test, and also the settings of the other factors that aren't involved here. And this has to do with something called interactions, and interactions are frequently common in nature. So instead we use a different way. I can just illustrate it very simplistic. If we would have done a design like this, we would have been able to see this is the best experiment, this is the worst. We can mathematically model in what direction to go to find this optimum. We cannot do that if we change one factor at a time only. So the total idea is to do fewer experiments and get more information, more accurate information. Also, design experiments will enable you to claim that you have the causal relationship between the factors you're looking at. So very important. So the background here is that I wanted to try a few things. And I will tell you in the end why I chose these things to look at. And the things are like creatine, protein, carbohydrates, how they influence blood glucose. So what we did is that we took and measured blood glucose and beta-hydroxy, which is ketones, 1 hour after ingestion of a number of different things here. And you can see that we varied creatine from 0 to 6, whey protein up to 30 grams, maltodextrin up to 40 grams. Bulletproof Coffee was from 0 to 1 gram, or portions, it was one portion or not one portion. So that is coffee with the butter and the MCT oil, and you can find the recipes here. The MCT oil used in both cases were brain octane, and you can find the bulletproof recipe here. If you download the PowerPoint, you can click on the link. We probably can just search on this name as well. And coconut oil. So that is what we want to see. What happens when we take these according to design? Not just take them one by one, then we get one result. What happens if we take them according to design to reveal if there are interactions between these? Are there ways we can take carbohydrate without raising blood sugar or without breaking ketosis, for instance? That is some of the questions I wanted to have answer to. I also wanted to have answer to why in some clinical studies they see people lose fat, and in some others they don't when they look at weightlifting. And I suspect that has to do with the combination of these nutrients. And this study actually confirms that. We will look at that in the end as well. So to complicated things, we have two people doing this. One of them I wasn't really clear in my instructions. So one of them did it in the way intended, and one of them did not do that. So one of the individuals used bulletproof coffee with butter, but took the MCT on the side for some experiments and not in some. So the MCT was not in there as the recipe says. So that made the interpretation a little bit more difficult, because I would have wanted both to do the same experiment so we can see if there's any difference between the individuals as well. But it also gave us more information about the bulletproof coffee, even though that was not the intention of the study. The design matrix were still orthogonal, as a mathematician will say. And these are important things because then you can claim what you see is a causative effect. You do not confound your factors or your interactions. Once again, you can read up on if you want to know the details about design experiments. So I did a global model for both these individuals, then I did separate models for them each. So I will go through the global first, and then we can look at the others a little bit shortly. You can download this PowerPoint and look more on the details as well. Send me an email if you don't know where to download it. We will put it up somewhere. I haven't decided where yet. So first, a look at the raw data. So this is just the glucose. The difference, what I model is like the difference. Will glucose go up or down? In that way, we take away some of the starting levels. Some people might be low in glucose in the morning, some are high. So I've looked at the difference. Will it move up or down? And model that. You can model the end result, the absolute value as well, but you don't get, the models are good, but they are not excellent in that case. And the ketone difference, will ketones go up or down? The blue ones here are replicates. In total there are like 35 experiments done, whereof 4 of them were done. They did about 16, 17 each. In total it's 35. 4 of them were done identically. So you can see here on the blood glucose number 2 is there are 2 squares here. They're on the same place. So they were very reproducible. Next experiment here, number 3 and 20. Fairly close together, but some difference. This one, number 5 and 22, they are identical. The system recognized that automatically. The design is identical, but the outcome, of course, is not identical. Here you see some more larger difference between the individuals. And here they are close together again. Ideally, we'll have this duplication all over here. But now we just have it for 4 experiments. And the same for the ketone level. What you want to see here is that the difference between the individual are smaller than the difference between the high and low value here. Because if the difference is equally large here, or larger, that means that you can't build a model for them at the same time. There will only be noise in there. The noise level between replication of experiment is higher than the variation. If you like statistics, you will see that if you look at this ANOVA table. If you don't like it, don't worry. We will figure everything out here. So, did we get any good models? Yeah, the global model is very good. Everything is relatively, of course. But there will, of course, there were risks we won't get any models at all. Maybe there is too much noise in the system, or everything depends on everything. But the statistic clearly shows that we have reliable models, down to a certain level at least. And here you can see something called R-square, and this is the cross-validated R-square. So R-square is used in all publications when you build models. This cross-validation is not so often published, but in industry it's essential because it tells you if the model can predict for real or not. You can get a high R-square, but have this one on 0, and then it's useless anyway. So what does this mean? For instance, if you have an R-square of 0.8, that means that 80% of the variation in glucose here is explained by the model. 20% is unexplained, basically noise, day-to-day variation, but also between individual variation, because we have 2 individuals here. And that's very good, actually. That's very good numbers. And the same for the ketones, also in the same area of 80%. The cross-validation is lower, but you remove some data points from the model, so it becomes weaker, and then you predict these. So it's a smart way of internal validation of a model. So the real value is probably somewhere between these two. Once again, if this was a publication, we would have need to show this. They will accept just the R-square. They don't even ask for the cross-validated values. If we get more people doing this, now it's only 2, I will try to send this for a peer-reviewed scientific journal to see if we can get it published. That will be really cool. This is the same type of plot, but instead it's visual, so you can see instead of getting just a number. So this shows the observed versus the predicted. For a perfect model, everything is on this line, but you can see there are some day-to-day variations that makes the model isn't really able to predict everything to 100%, but as I said, to 70-80% it predicts correctly. You can see here, for instance, one value that's a little bit off. Might be a reason for actually looking into that. Maybe a mistake was done. Maybe the ketone measurement had a bad day or something. You were eating something unusual the day before or so. Okay, so now to the interesting part. What did we get out from this? What factors influence the glucose and the ketones level? So if we start with the glucose, so this is the difference in glucose. I do have a few slides later on the different units. We are using milligrams per deciliter, which is more common in America. So you have that in the report if you want to prefer that. Here anyway, what this says is if I take maltodextrin, if I take the amount used in the study, that was 40 grams, the largest amount. If I take 40 grams of maltodextrin, the blood glucose will increase almost 3 units. It sounds very reasonable. If I take Bulletproof Coffee, and here it's breaked out, so this is Bulletproof Coffee with butter. The brain octane, the MCT, is in here as a separate factor. It will decrease the glucose. Whey protein, the same. On average, it decreases glucose with 1 unit. And then we come to something interesting. Whey, and there is like a multiplication sign here, and maltodextrin. So that means there is an interaction between whey protein and maltodextrin. And this means if there are no interactions, I can take this value here, like 3 plus minus 1, that is 2. So that means if I take whey protein and maltodextrin, I will have this increase instead, 2 units. But the interaction here says if I take them at the same time, they interact, so I have to reduce another 1 unit of glucose. Then we're down to 1 actually. That will be the expected outcome. So if 1 plus 1 is not 2, then we have interactions. And as you can see, we have plenty of them. And the only way to estimate them is by doing design of experiments. Cannot estimate them if you change one factor at a time. So they're very important if you optimize things, because then you want to have a correct model. And then something, this I expected, and I will explain later why, but then something kind of strange. There's an interaction between whey and the brain octane, actually telling that that combination will kind of increase glucose. Now this was only done by one person because they didn't do identical experiments. So I would like to see a few more do that before I perhaps says it's something that is true for the general public. But it's quite interesting because I do know most people really like the Bulletproof Coffee, but some say they feel not so well from it sometimes. It might be that there are some interactions here with whey, obviously, but maybe for other proteins. And perhaps if they take that pre or post within a certain time, they get this interaction and kind of diminish some of the effect of the Bulletproof Coffee. Coconut fat has the total opposite interaction with whey protein. It actually decreases blood sugar. MCT or brain octane, which was used in both cases, decreases blood sugar. Creatine and maltodextrin also has an interaction, basically telling that creatine protects you from carbohydrates, which I also suspected, and I will show you a study why I suspect these things. They have not been tested or documented before in any publications I have come across, but there are indications this is the case. And whey protein and Bulletproof Coffee, that is just the coffee and the butter, as an interaction. Creatine might decrease glucose slightly as well. Coconut is actually not significant. You don't see that on the plot, but I have other, I don't show you all the data. But you have values for the significance of these as well. And then for the ketone, the same. It's like the opposite. If I take maltodextrin, it goes down quite dramatically. 0.65, 0.7 units. If I take brain octane, it increases 0.5 almost. Bulletproof Coffee, and that is just the butter and the coffee, also increase ketones. That's quite interesting. I don't know if just butter will do the same, or if there is something magic with the coffee here. Once again, the intention was not to look at the coffee, but we just got some additional information because of the deviation from the protocol. And then you see maltodextrin and coconut oil. If you combine them, they actually decrease ketone more than they do separately. And then you see whey protein and MCT have a synergistic effect on the ketones. But you saw here, so it's kind of a, yeah, there might be some biochemical explanation to that. I will leave that for now. But it was not what I expected, originally at least. Whey and maltodextrin also increases synergistically ketones. Not as much as here you have the brain octane and bulletproof coffee. If you add them together, you will see a huge peak here. So that's a good combination, obviously. Creatine seems to increase a little bit, whey protein as well. Coconut oil is not significant, nothing happens. So that is how we interpret these things, and you can see the level here as well. So if it says here 0.5, that means that it will increase 0.5 if you take whatever is down here, which is MCT oil. And obviously then if you don't take it, that will compared to when you take it, it will decrease instead. So all of these are interpreted as, if I take this, what happens? Goes it up or down? Well, it goes up. If I take this, what happens? It goes down. The direction here shows you, and how much. But then you also have to account for the interactions to get the full picture. And here you have this in Word in case you want to see. Then we did the individual models as well. I will let the individuals look at these. I won't go through them in that great detail. I can only conclude that one model here has very high values, like 95% of the glucose value is explained, and that is for HD. And also for ketones, very high accuracy on the models. I guess the reason why this model isn't equally high, it's better than the global model, but there are two main reasons for that. One is that there are more non-linear relationship for GH. I can see that, but we didn't do a model that support to find out which factor has a non-linear relationship. Simply because I thought the design was small enough to not get into this trouble, but that was incorrect. Basically, if we take maltodextrin from 0 to 40 grams, if we would have chosen 20 or 30 grams, it probably would have been linear, but 40 was too much. So this person is a sensitive person that easily feels changes. You can add the data, the experiments to model nonlinear terms. It's just that would have been another 10 experiments, and I thought people would be too much for everyone to do. But we did add one just to check if we have nonlinear relationship, and we do have that. We have it here as well, but they're not as profound. They're much larger for GH compared to HD. It might also be so that one of the experiments are a little bit odd, incorrect. Maybe the day-to-day variation, one day, whatever you did the day before, or maybe the glucosometer had a bad day. It might be one, and I will look into which experiment might be worth to redo. You can see, you have different ways to have a guess there at least. You might not, don't know for sure, but you can see on the cross-validated residuals which experiment seems to be not in line with others. Here you have the observed as predicted. Excellent here. Everything is on a straight line. You can see number 17 somewhat below. You can see here it's a good model. It's very significant. But you can see that 17 here is quite far away. Here it's slightly away. It's quite far away. And this experiment number 17, that is the center point that tests if we have a linear model or not. So if it's linear, that one should be in right on spot in the middle here, but it's below here and it's below here. So they have slightly nonlinear relationship here, and here you have more profound nonlinear relationship. This is due to the sensitivity of this person. It basically means that this person can, GH here, can reach the same result but with lower amount. He can take perhaps 3 grams of creatine instead of 6, or half the amount of brain octane, and get the same results. That is what it says. Because it's below, it would have been above, it would have been the opposite. Nothing happens until he reaches the maximum amount. Here's the opposite. Things start to happen quite early. But we don't know if it's for all factors or just one of them. We need more experiments to say that. But it's still, all interaction and everything here is still valid. It's just that it slips a little bit in the nonlinear relationship. Here's another way to look at it. You can see that if I draw a straight line between these two, 17 is below here. So if we would have moved these experiments and done them here, and the center point between it probably would have been between. Here I will need to draw a bent line down here, and then up here again. And this also, by the way, explains something that can be interesting to look at. If you look at the experiments for GH, you can see that, let me just open up that. You can see that there are some differences between the individual test of whey protein and the models claim about whey protein, and I will explain why that is. If we look at the design, whey protein is on 0 8 times, and on 30 grams 8 times. That means that we have 8 experiments low and 8 high, and the model will then take what is the average outcome of whey protein. Does it increase or decrease glucose? And the average outcome is in both persons that it lowers glucose, blood glucose. But that's based on 8 experiments on one side and 8 on the other, so 16 in total. And it's the same for creatine and all factors here. We have 8 experiments high and 8 low. So it's the average of that, which of course is much more relevant than just one of them. But that's the beauty of design experiments, that you can kind of reuse the same experiments to do testing in all directions and get a lot of confidence in the results. But there is something that might be a little bit confusing here. That is, if you only take whey protein, glucose went up for this individual a little bit. But the model says that it should go down. You can see that here. And that is because the model based this on all the experiments, not just that one individual. You can see that also in the raw data. Here are 8 experiments without whey, and the average is probably here, 3. And here are 8 experiments with whey, and the average maybe it's 1. So it goes down on average. But there is some particular point here where it actually might go up, but on average it goes down. And that's more practically relevant. If you eat other types of food, you want to know what happens during the day if I take something. Otherwise, you will just know what happens if you are in fasted state. Model can tell you that also, but it depends on. The more accurate model is, the higher R-square you get, the more details you can see. So it always starts with the average, the general trends, and then you add interactions and refine it to look at the details. And here you have the individual, and it's the same thing, the same interpretation. So I will and they're consistent. It's maltodextrin, it's Bulletproof Coffee. They're kind of similar. There's some differences in interactions, but that is also they didn't follow the same protocol for everything. So therefore we don't get exactly the same interactions. And here is for GH, and we also have here in milligram per deciliter. So the benefit of having glucose in millimole is that ketone is in millimole, so you can compare them. If I have 4 millimoles of ketone and 4 in glucose, I have the same amount in my blood of both, for instance. And mole is simply the number of molecules. It's like a billion. Well, actually it's with 23 zeros, but it's a unit. How many glucose molecules do we have, or ketones? So it's a number, like a million, but it's mole for 10 up in 23 approximately. And glucose here is it's in weight instead. So this is weight, and this is the number of molecules, and this is the weight of the molecules. So it's nothing more magic than that. But different countries have their own preferred way of reporting results. Chemists always use millimole. Nutritionists and physicians prefer this because it has some logic to it, because if you have 100 milligrams of glucose per deciliter, that means you have 1000 milligrams per liter, and that's 1 gram per liter, which is 3 or 4 grams if you have 3 or 4 liters of blood in your system. So that tells you how little glucose there is in there. Just 1/10 of a piece of bread will actually be all the carbs you have in your blood. So you will double that amount just taking a few chews on a piece of bread. Just to put things in perspective. And here to something interesting. This is a publication where they've looked at strength training, and they did measure body composition as well. And they have seen the things many times. And that is partly why I wanted to do this study. You can see here, if we look at fat mass, people that took protein post-workout, and they were eating more or less the same, they decreased their fat mass, and they became stronger. That's quite usual in all these studies. In this study, they didn't try carbohydrates alone, but usually people get a little bit stronger, but a lot fatter when they take only carbohydrate post-workout. But they did try protein and carbohydrate. They also became stronger. Not as strong as the protein group, but almost. But they also added a few pounds of fat, or it's kilograms. And that's interesting. So protein and carbohydrates. Carbohydrates obviously make you fat. We kind of knew that, but even post-nutrition, this study says. And there are more studies, exactly the same result. But then the interesting thing happens. When you add creatine to the protein-carbohydrate mix, they didn't get fat. They might even lose some fat. So that tells me that it looks like there's an interaction between creatine and carbohydrate, that creatine protects you from carbohydrates. And if we look here, we see creatine, maltodextrin, an interaction between the two, telling us that in the presence, creatine itself has no real effect on blood glucose, but in the presence of maltodextrin, it suddenly will protect us. It will lower blood glucose. And obviously, high levels of blood glucose will lead the body to store more fat. You might argue, well, post-nutrition, there is not much insulin needed and so on, but insulin also signals to store fat. But glucose does that independently of insulin also. You can see this as if you live in a building that is like the cell, someone knocks on the door, that is a hormone, knocks on the door and tells you to do something. But the door is locked, so you can choose to act on that or not. And that's exactly how it works inside the cell. Inside the cell, there are also mechanisms that decide what to do, if to store fat or build muscles. And inside the cell, they can overrule whatever information comes from the hormone system most of the times. Unless it's a hormone going to the nucleus, because then it goes inside the cell. But so basically here, if you have higher levels of sugar in your body, it doesn't matter if you have insulin there or not, it will still lead to weight gain, fat gain. And the opposite is true if you only have insulin present without sugar. It won't actually stop fat burning, insulin itself. That has been tested when they gave people, well ketogenic adapted people, injected insulin to them. That should have stopped their fat burning. And obviously glucose went down to 0. The fat burning should have been stopped, and that would have led to a coma quite quickly. But it didn't, nothing happened. Because inside the cell they said, okay, now some stupid man outside here wants us to stop burning fat, but we don't have any sugar, so we won't stop burning fat, because that's all we have. So they didn't listen to that signal. So whatever happens inside the cell can overrule what happens outside. It's a generally good rule to think of. So it fits very well here that creatine protects you from carbohydrates. And we don't have in this study, but in other studies they have just pure carbohydrate as well, and then they gave even more fat compared to when you have protein in there. And we see that as well. That you can see that the whey, where's the whey protein? Whey protein has some decreases blood glucose, and you see there's no interaction here. I thought there were. Okay, so it's a little bit different between the individuals here. Yeah. Anyway, so whey protein also has a protective effect because whey protein lowers blood glucose, and whey protein and maltodextrin has also an interaction. It is for this individual, obviously not for this one. But regardless of that, whey protein lowers glucose. At least some people, I would actually guess all have it, but as an interaction between these two. And there also is an interaction with creatine and carbohydrate. So if you add that all together, you can ingest carbohydrates and get away with it. That's the conclusion. So I think that's very interesting that our small study actually support what we can see in large clinical trials. And the ones that are doing these clinical trials, they don't really know why they see what they see. Because they don't look at interactions. They don't do design of experiments. But if you put it all together, it makes sense. And there are a lot more of reasons why I wanted to see this study. But that's one of them that I wanted to show you here. I also want to show something with you. These interactions, I guess, they're not so easy to understand if you're not used to them. You understand the concept, I guess, but really, what does it mean? So I will try to show you some pictures that might put a highlight of that, or you might be more confused. We will see. Let's look at both of these. Doesn't really matter what we take here. So, if we have no interaction in the system, that means that if I go from here to here, I will get the same results as if I go from here to here. Obviously, that isn't really the case here. There are some differences. And what does it plus say? As it tells us that if I take maltodextrin, blood glucose will go up to the red here, 40 grams. Or if I take 25, I ended up here. And you see the level here is 2.5 increase, 3 up here. If I take creatine, it will slightly decrease a little bit at least. And you can see the same for ketones. What happens if I take ketones? Then ketones go down with this level. And if I don't take them. But look at this picture now. What I want to show you is, you see there's some interaction here because these aren't identical on this side and this side. There's slightly angle here, they're not horizontal. If they're horizontal, you have no interactions. And here, but here we look at creatine and maltodextrin, we also have settings of whey, Bulletproof Coffee, and MCT. So if I change something, I just throw in some whey, what happens? You see it change shape. You see that? So here it's mostly red here. You see how the shape is? I throw in some protein and it changes to this corner instead. I throw in some MCT. Oops, change even more. So where you want to be here depends on the interactions. So in this case, for instance, if I take no maltodextrin, no creatine, and these settings, I will end up here, lowering blood glucose. But if I want, if I want to have Bulletproof Coffee without brain octane, it will look like this. If I have whey protein also, you can see this one becomes very strange. So over here, I'm in minus 0.25, and here's minus 0.1. Whereas if I add the MCT, the brain octane, it changes shape. And that is due to interaction. Otherwise it will look the same shape, it will just be more or less blue, but the lines wouldn't change direction like this. All of that is interaction. So this really you can use as a tool to map how do I decrease glucose as much as I can. Given if I have no carbohydrates in my diet, or given if I have carbohydrates, the recipe will be slightly different, actually. And that you can see here. So that was just to give you perhaps a better understanding what interaction is and how they influence the system. It's simply that they change the way things look. And you can't see that without doing design of experiments. Yes. So that's it for now. I will really encourage everyone to please, some more people could join and do some experiments so we can validate that this model we have here, we can refine it, and we can say that this is true for a large number of people, perhaps not just these two that have sent in results. If you have questions, you can email, you can send on Bulletproof Forum or publicly or in private to me, or try to answer them. And also if you have other ideas, we can do these designs within other areas. It will be very interesting to answer them. And also if you have other ideas, we can do these designs within other areas. It